Welcome back to the course, continued course on statistical mechanics, and I hope you are having fun. And good morning or good afternoon wherever you are. And so we continuing with the basics, and we did the monatomic gas in a very detailed form. The reason of that, I wanted you to go through the working of monatomic gas, and it is not just monatomic gas is the simplest system, but it also you get the beautiful wonderful stuff that is used repeatedly, which is kind of unbelievable that giving that it is such a simple thing. But then I always draw the analogy with quantum mechanics. In quantum mechanics you have simple systems like particle in a box, harmonic oscillator, rigid rotator, but those three models play enormous role in condensed matter physical chemistry, condensed matter science and physical chemistry. The particle in a box, goes over to be used in explaining spectra of conjugated polymer like butadiene and length dependence, that 8 ml square term. Then it goes on to use, as I showed in the last class, to the density of states, and that is the model of free electron gas, a very well known model, and with its root over energy dependence of density of states, and that plays a very important role. So, this is amazing that how, so if you read the book that is given was done by Feynman, Statistical Mechanics, you will find that, and also Landau-Lips's Statistical Mechanics, these two are the best books in the field in earlier things, who dealt with foundations and earlier parts. So, then you will find that amazing that how much importance these very simple results find in those books of those masters. So, now I want to spend some more time with diatomic gas. We have again done it little, but we didn't little in a hurry. Now I want to review, and now again it is kind of, you can say that we did first, as my analogy of painting of a wall, we do it in not in one shot. You paint it once and then you paint it again and wait for a time, let it dry, then you paint it in the final coat, usually the third coat that comes. And through that, the way our mind also works is very much like that, we get into. So, now we will do the ideal diatomic gas. Look at the term that it is ideal, ideal, and that it is diatomic. So, now we have not monatomic spheres, but we have molecules like nitrogen, we have oxygen, this kind of molecules. Then we will do polyatomic also, which will particularly we talk of water, and we will talk of ammonia and some other molecules. So, first we will do diatomic, then we will do polyatomic, and the equations you might have seen before, but it will be done more rigorously now and more connection to the real world. Okay. So, let us start then. So, we now have, in case of molecules, that these molecules are more realistic systems, and that they continue to have the if this is the diatomic molecule, they continue to have translational motion of the center of mass, but they are also vibration, they have vibration and they have rotation. Okay. Now we have to translational part we have done, and we can now, you have done probably a lot of these things that you go to a reduced mass description, where I can consider translation is that of the center of mass with m1 m2 by m1 by m2, the reduced mass of that, and if they are the same, then it becomes half. But we do have to take care of now rotation, and we do have to take up vibration, and as I repeatedly say, we will again go back to quantum mechanics and find the energy levels from the vibration and rotation, and we use them. We can also do it classically. We can also find out the rotation, rotational kinetic energy and vibrational kinetic energy, and you can integrate them the same way we did in translation. However, in translation we did both classical and quantum. See, we basically did classical when you evaluate the partition function, but when you went to density of states, we did quantum. And one can show, if I evaluate the partition function from the quantum particle in a box energy levels, then high temperature limit, I will go over to quantum mechanics, that you can work it out yourself, or we will do somewhere down the line. However, in the rotation and vibration, things are a little bit dicey, particularly in case of vibration. In vibration, vibrational frequencies many times in thousands of centimeter inverse, like OH stretching is 3600 centimeter inverse. And you know, one cavity at 300 Kelvin is 206 centimeter inverse. So now, thermal energy, so the energy of these molecules are 15 times more than thermal energy. So that means gap between two vibration energy levels is 15 times kVt, and that you cannot treat by classical mechanics anymore. So energy levels are discrete, and you have to do it quantum mechanically. And the situational rotation is not that adverse to classical mechanics, but it has also need to be treated quantum mechanically, particularly in low temperature. We will see high temperature you can still get away by doing classical mechanics, but not at low temperature. So then also, as we said, that many we need the talk of vibrations in many things, and again what we learned from the class is simple non-ideal diatomic and polyatomic gas, we will go over to very complex systems. That is my reason to do these systems repeatedly, because in this, in chemistry, in physical chemistry, we need this much more than a physicist need. Physicists don't need them that much. Physicists very easily go to interacting systems and they do a general phenomena like phase transition. But we in physical chemistry, we think of the molecules, they are flowing from one part to the other, they are undergoing a chemical reaction, and when they undergo a chemical reaction, then entropy changes, the amount of entropy changes in a chemical reaction, or the vibrational degrees of freedom that play a role in chemical reaction, or vibrational spectroscopy, rotational spectroscopy. So we are more in the microscopic world, and we explaining, our mandate is to explain these properties, and that require a much more detailed understanding of the spectrum. So let us continue then with this after this motivation. So let us consider just a diatomic, you can consider nitrogen and oxygen, then we have translational degrees of freedom of the center of mass, that is 3. Then it rotate like this, in a linear molecule it can rotate like this, it can rotate like that. This rotation is not, doesn't change anything. So we have 2 rotational degrees of freedom, and we have the stretching, vibration, and the vibration degrees of freedom. The total number of degrees of freedom is 6. And then there is interesting things that come in, which as the experimental observable things, and gives us very important properties. So one of the reasons we are so interested, physical chemistry is so interested in vibration and rotation, is that there is through vibrational spectroscopy and through rotational spectroscopy, some of the things which we can access to, like anharmonicity of vibrational frequencies experimentally, we get through a vibrational spectroscopy. Then the molecules are not harmonic. We will assume here harmonic, but they are anharmonic, otherwise they won't undergo a bond breaking event, as all of you know. That information about the anharmonicity, how when you puts them away, how the bond weakens, is very important quantity, that we get through vibrational spectroscopy. Then rotation, when molecule rotation, they rotate very fast, they get couples to vibration and called Coriolis coupling. That is a very important thing in the bond breaking event in atmosphere, high up in the atmosphere, when molecules rotate very high temperature, rotate very fast. So those are the things, are the mandate of a physical chemist, and that's we are, and so those very important information of the anharmonicity or rotational coupling constants, we get it from this study that I am going to tell you today. And these are the things I did not tell because I did not want to burden you, but now we have to do these things and get the what is called the A out of these, the real fruits of our study. Okay, so we are talking of ideal gas, we are talking of molecules right now not interacting, that is the kind of things I said here, that they interact, the coupling, between that, but we are going to ignore that now, and we are going to do with the non-interacting. So, your ideal gas and the rotation, translation, vibration are not interacting with each other, and there are actually these interactions here become very important, but we will do that later. So, if I do not consider the coupling, then I get a very nice decoupling, because energy levels are not coupled to each other. So, remember my total partition function, molecular partition function of a single particle, that is why I use the notation small q. M stands for molecules, then my qm is sum over all the energy levels, not energy states, each individual energy level. We have to change that later as we go along, and then the energy is sum over rotation, vibration. So, energy is sum over E I rot plus E vibration plus E rotation, vibration, translation, and plus E electronic. That is so, then these are separate sums, so they go into a product. So, total molecular partition function is product of partition function of electronic, the translation, rotation, vibration. Now, as I said, much of these studies at room temperature, ambient conditions, the electron is in its ground state unless they are electronic transition optically excited, which is again a very huge branch of physical chemistry. If not, then we are looking at a large separation between ground and excited electronic states, and that does not affect the thermodynamics most of the properties. So, we can ignore that. So, we do not need to talk of electronic right now. Then my molecular partition function become product of translation, rotation, vibration. We already have done translation. Now, we will go into do rotation and vibration, and we will do the vibration first, and then we will do the rotation, and you will see a lot of very interesting things that I will talk to you today, which I have not talked before, and they are amazing, particularly the amount of results we get and the natural phenomena we can directly access to by the vibration part. Just translation, I told you that it is very application, but here you will see even more dramatic things. Okay. So, now we start, we can write the vibration of Hamiltonian. Before we go to partition function, we need the Hamiltonian, and then we need the energy levels. So, vibration is this half mu square. You can write it many ways. You can write half many times. We write half omega square x square. That is my favorite vibration on Hamiltonian, half omega square x square. Okay. So, okay, all right. So, now the quantum partition function is when you have almost atomic molecules. This is very important, as I was taking that, for example, for a vibration of frequency 3000 centimeter inverse, the energy h nu is a vibrational frequency in 15 kBt, and water OH, the symmetric vibration they are together going like this, symmetric, that is 36, if I remember correctly, centimeter inverse, and 1 kBt equal to 300 Kelvin is 206 centimeter inverse. So, we are talking of 36,000 centimeter inverse versus 206 centimeter inverse. So, you are 18 kBt. Then this bending is about 2000 centimeter inverse. So, we are talking of 10 kBt. So, these are very large numbers. That means in vibration energy levels, now vibration energy levels. So, if I talk about vibrational potential in surface, then vibration energy levels, this gap is say 15 to 20 kBt for water stretching, and for bending it is you have about 10 kBt, where T is 300 Kelvin. So, this gap is large, is the 0 point vibration energy, and this is the first one. So, this is the scenario we are looking at, and you have to we cannot do classical mechanics because classical mechanics, what does classical mechanics say to you? Say energy levels are continuous. So, I can go from one energy E to next one a small amount by hundredths of kBt, 1/100th of kBt or something, but that is not true. That is true in translation, where I have the next energy level just sitting next to it of the odd, but not in A, not in vibrational, and not even in rotation. Here the energy levels are spaced so wide that I cannot consider it to be continuum. So, then I cannot do classical mechanics. This is a prime case where I have to do quantum mechanics, and the quantum mechanics aspect plays extremely important role, and that we will see very quickly. And most of the results that we do vibrational degrees of freedom, even thermodynamics, using classical mechanics by using half kx square. So, I write half kx square, then I write my Hamiltonian is vibration plus then p square by 2m. So, and then I do the integration by writing the partition function, molecular partition function, and doing integration there. I am just doing one dimension, one particle, and dx dp e to the power minus beta h, and then this double integral I do, and I have both x and p as a Gaussian. I can do the integral. That is a trivial actually, 2 Gaussian integral. So, one again is half kx squared, no longer volume because the particle is now constrained. Particle is constrained by this potential. So, then I get root over pi k by a, root over pi m by k, and then this is again 2 pi m kBt, that 2 pi kBt by k from this term and 2 pi m kBt from this term. That is a classical partition function, which is trivial. And that I telling you it does not work, it does not work in most of the cases. So, we have to do the quantum mechanics. So, this kind of classical approach, which is trivial because I have such a simple Hamiltonian, and I can integrate and get the molecular partition function, then go on and put the capital Q and then A equal to minus kBt ln k, and I can go on doing my rest of the stuff, but that does not work. So, now we have to do a little bit more. So, now in quantum mechanics we know the harmonic oscillator. So, these kind of energy levels that we have, Schrodinger solved the system for us, like he also solved particle in a box. One of the reason in quantum mechanics textbooks, as I probably told you before, that you do not see any name all the way in hydrogen molecule, because Schrodinger solved all of them. There is a very nice book, collected works on quantum mechanics by Schrodinger, and where you see that he has solved everything, particle in a formulation of Schrodinger equation, then solving it for particle in a box, then solving for a harmonic oscillator, solving for rigid rotator by a hydrogen atom and hydrogen molecule, all the way, these 5 problems. I got that book very cheap in our Calcutta Presidency College bookstore by paying a couple of rupees, and this is a wonderful position that I had, an old book, somebody bound it, and there are some kind of notes here and there, but that book was the eye opener for me, that it was, and I felt much more understanding of how quantum mechanics developed, and is a very important historical statement. However, now coming back, we use Schrodinger's result for statistical mechanics, and here are the energy levels of harmonic oscillator. That energy levels, this is a 0th energy level, the 0, 1, 2, and this, and the energy of this is half h nu, and then and this is 1 plus half. So, is half h nu, this is 3 by 2 h nu, this 5 by, like that it goes. I have to add it up now. So, the vibrational partition function is sum over this n 0 to infinity, I have up all the way, n plus half h nu the 1 by kBt. This is my canonical single vibration partition function, canonical partition function, and I have this, that is why the temperature T is coming. So, that means my this harmonic oscillator which is oscillating here. This guy is oscillating, but this is in a temperature bath with a temperature T. And temperature T plays a very important role, because that allows the relative, because of the energy gap, relative weight of the different energy levels. You can easily see why the many of the cases this particular zeroth order energy level plays such an important. That's why in vibration such a big deal to zeroth vibration level has been such a big deal for many other reasons, but in thermodynamics that's very important. But even then, even at zero vibration level, it plays a very important role. So now I can do this calculation, because I take the half out. So I am going to do that, this h nu by 2 kBt. So Q vibration is e to the power minus h nu by t, then I have a 2 kBt here missing here, I have 2 kBt, then I bring here, this is correct in book, but when it was transferred from there, it was this mistake was made. So now e to the power minus h nu by 2 kBt. So this is the sum that I have to do, and this is very easy, right? Because if I put x equal to e to the power minus h nu by kBt, if I make that into x, this is if my x, then I have partition function becomes e to the power minus half h nu by kBt n equal to 0 to infinity x to the power n. Good that it starts from n equal to 0 to infinity, and I know that this series when x is less than 1, this is nothing but 1 by 1 over x, all right, and good. So now this is become mine. So this h nu by 2 kBt, that is in front, that comes h nu by 2 kBt, and this sum which is the geometric series becomes 1 minus x, and x is e to the power minus h nu by kBt. So this is my partition function, beautiful and neat expression. And actually in this case Schrodinger did all the work, giving us these beautiful energy levels, and now we will have a lot of fun with this expression. So this is now my partition function, and I am going to do some thermodynamics with that now, because I now know how to do extract free energy from this. I know how to extract entropy, I know how to extract specific heat, and specific heat transfer, and entropy also turns out to be explained. We wrote a paper last year, long paper on water, and the whole thing of calculation of entropy of the vibrational modes of water, but those are intermolecular vibrational modes, but low temperature solid, this thing we will discuss now, and we will probably discuss more later, but we will discuss, certainly definitely discuss it now. So now this beautiful expression that I have here, I am going to use that. Okay. So again rewrite this expression, because we love this expression, beautiful, e to the power minus h nu by 2 kBt, 1 minus h nu by 2 kBt. So characteristic temperature, now I introduce one thing, I realize that h nu by kB, remember kBt is energy, the dimension of kBt is energy, and remember ml square mass by t square, the dimension of mass, length, and time. kBt is energy, h nu is also energy, h nu is also energy, both are energy. So now I realize then h nu by kB, h nu by kB has the dimension of temperature. This is the dimension of temperature. That is now that because this must be dimension of temperature, because it has to be dimensionless, because it is upstairs. Now I define a temperature, very important characteristics. See, it is very interesting. You have one universal constant, Planck constant, you have another universal constant kB, and you multiply it by frequency, and you get a temperature. It is a beauty. Planck's constant, Boltzmann constant, and the frequency. So together define a temperature, and that temperature plays a very important role. That temperature is denoted by theta vibration, is a vibrational temperature, that the how hot a vibration is. Now I can rewrite introducing this notation that e to the power minus theta by 2t 1 minus theta vibration by t. So, this is now my new my rewrite my partition function. Remember that it's a very beautiful thing, but remember that a factor of 2 is there. So, now I go and do the partition function. So, this is the Q vibration. Now, I want to go the free energy. So, free energy I know that there are n number of them. So, if number of n number of non-interacting identical harmonic oscillators. So, that is the thing. So, then my Q n is Q to the power n, and then I write free energy A equal to minus kBT ln Q, and that n comes out, this n comes out in front, giving me n here, and then kBT remains here. So, n kBT and ln give me ln e to the power by 2. So, this is just using the one previous slide or previous page and give me. So, now this is the, I will go back to theta vibration again. So, free energy now is I can do something more. I note that, remember that we have to keep track of this minus, I have to keep track of this minus. So, this part has two parts, one part is the numerator part, denominator part, and numerator part then ln exponential, ln e to the power minus x is Lx. So, h nu comes out, minus and minus becomes plus, kBT, the kBT comes denominator here, that cancels this kBT, I get n by 2 h nu. So, this is the first term that comes from there. Now, this comes in the denominator, the minus sign, that makes this minus plus, so I get a plus here, then I get n kBT, this n kBT here, and then ln 1 minus h nu by kBT. Remember that 2 is not here in the denominator. So, this is the free energy. So, free energy of a harmonic, n number of harmonic oscillator is given by this quantity. Okay, this is well and good, there is no need to spend too much time there. Now, I want to calculate the entropy, this is where the fun starts. So, I do that. So, my free energy is here, I take derivative with respect to temperature. Remember that has no temperature, this term has no temperature. So, that goes to 0, and then I have here I have two terms, one is that one is this temperature and this temperature here. So, when I take the derivative I get two terms, and that they are shown here. One term is this so, one term is just this term, I take the derivative with respect to temperature, this disappears and I just get this term. Other term n kBT will remain, I go and take derivative with respect to that. This is little complex because first ln x is 1 over x, so that will go in the denominator, then I have to go inside and take a derivative, and when I take a derivative, this term goes to 0, then this minus comes with the minus, but then I take derivative of that, exponential comes down, minus minus become plus. However, I have t in the denominator, so another minus come, minus t square. So, that minus will be carried through minus, but that 1 over t square, one of the 1 over t square get cancelled by t. So, I get 1 over t remain and Boltzmann constant gets cancelled. That what happened, and then when I do all that, so I told you one term is the first term that comes, and here because this is after taking derivative of exponential d by dx e to the power minus x is minus e to the power minus x. So, that remains from that term, and one, as I told you, one goes to the denominator, then goes to denominator, and there is one more negative sign here. So, what happens in that derivative? We have the, in the derivative we have the following thing. There is one negative here, and that get cancelled by this negative. Another negative comes from here, third negative, but then fourth negative comes from here. So, I get a positive term. So, this is my definition of the entropy. This plays a very, very important role in many, many calculations. So, let me so this is the entropy of the a harmonic oscillator, n number of harmonic oscillators. This the, look at that, is a very strong dependence on frequency nu, very, very strong dependence. It is in e to the power minus h nu, and this is over e to the power minus h nu. Now, when let us consider some things. First, the strong dependence on it, there is one term, then the enzymes and many, many molecules, DNA and many cases, the bond vibrations. This is something which is amazingly interesting, but we will talk of it little bit now, this particular issue. Before I do that, let me consider the following thing, that what happens when nu is small? There are some cases when nu can be small, like in iodine. In iodine, vibration is about 500 centimeter inverse. There are some vibrations which are even smaller, intermolecular vibrations, they can be smaller, of the order of 100 centimeter inverse or even less. Some collective vibration, and I'll now explain what is the collective vibration. Collective vibration, when you put many molecules together, then their translational modes, they are constrained, their translational modes are got, but number of degrees of freedom must be maintained, right. So, say I have n number of molecules put together, there are 3 n vibration, then we know that they become 3 n minus 5 if linear, 3 n minus 6 if non-linear degrees of freedom that come. So, these degrees of freedom go over to the we call them intermolecular vibrations. So, they could be rotation of with respect to each other, like consider C still being, then there are rotations of this kind, or even long polymer chain. There are many, many motions which are bound motions, but they are very low vibration molecules. And so, then they can be low vibrational, low frequency modes, and then you can start playing certain games. You can say, okay, if nu is small, let me consider nu is small. When nu is large, then we can easily see, when nu is large, temperature kept fixed, then e to the power minus h nu by kBT goes to 0, and I have ln1, and ln1 goes to 0, and then I have, okay, I go to nu very large is this quantity would go to 0, and then I have this quantity goes to 0, I have only 1 compared to 1, this is small, h nu by kBT is large, again h nu by kBT large means this term goes to 0. That means, if I look at the limit, large frequency limit, that h nu by kBT much greater than 1, if I look at that limit, then this quantity goes to 0 because of this small quantity in front, but this e to the power minus h nu by kBT will kill it, this will go to 0. So, this term will go to 0, h nu by kBT will go to 0, will become very small, I have left with 1, and as already described in 1. So, entropy is going to go to 0. So, entropic contribution of a large vibrational mode is negligible. That is why many, many times in molecular calculations, we do not consider the contribution of entropy of vibrational modes. This is a very important statement that I am making. However, that is not the case in this case of collective modes that I said. In the collective modes, now let us see that low frequency modes that come in. What will happen in low frequency modes? Now, let me consider the other limit that h nu by kBt is much less than 1. Believe me, there are cases like that in collective modes. In water, in many cases, they are 10 centimeter inverse, 20 centimeter inverse, and in solids, less than 10 centimeter inverse modes are there, and they play a very important role. Amazingly, nobody thought that they will play such an important role, but they play important role, and I'll come to that in a minute. So now, when now nu becomes very large, then I can expand that. I now say h nu by kBt is small. I can expand e to the power minus x, and that e to the power minus x I can write as 1 minus x. This one cancels this one, and this becomes plus x. So I have n kb h nu by kBt. kb gets cancelled. I have h nu by t sitting here, which is nothing by I have done it before. My h nu by t sitting come in front. Now let us look at this quantity. Now nu h nu by k this is small. So again I can expand that. So this will become 1 minus x, 1 gets cancelled. I have get h nu by kBt coming out from here with a plus sign in the denominator. This h nu by kBt, I said 1 minus h nu by kBt, but since h nu by kBt much less than 1, I can neglect the next term. So now h nu by kBt that so I have 1 only from numerator. Denominator I have h nu by kBt, and that now cancels h nu by t, and I am left with a kb term here, and that goes upstairs. So it has I get just a kb contribution from the entire things, and I get a contribution from here h nu by t from here. So low frequencies have a very different contribution to entropy. They come up with a significant contribution. So while high temperature, high frequency modes make no contribution to entropy, because h nu by f, they are all in exponential. However, they are all in exponential like this term, but in a low frequency, as I just discussed, a significant non-zero contribution comes, and that play extremely important role. And that is where these seemingly trivial calculation that we are doing played an enormously important role in understand in a very large scale, important phenomenon, and that is nothing but specific heat of solids. Now, specific heat of solids, low temperature solids is an extremely interesting thing.